Good morning, everyone. I'm Philip Griffiths and would like to introduce our first speaker this morning, Boris Zilber, who will give the second of his lectures, actually short course, on From Logic to Geometric Stability Theory and O-Minimality. Boris, the floor is yours.
Yeah. Thank you. So we are on the last slide that we finished last time. We finished yesterday, and so I also showed you a online classification site that to me looks like a little bit like well, I would like to see it as a kind of Mendeleev periodic table for mathematical structures. And yeah, so one subclass of the structures that we specifically interested in this workshop are O-minimal structures. But what I want what is it that I want to deliver. The idea is that in fact it's quite important to understand the place of O-minimality in this classification and very interesting relations to many other classes and specific structures in those classes. Okay, so now after we talked that much about general classification theory, so I will concentrate on something that we often call fine classification theory. So it is something that we kind of look through magnifying glass into a specific kind of structures, which are, we call them minimal structures. And the shortest way of understanding where this minimal comes from is that it is a minimal dimension for infinite structures. So it is dimension 1 structures, in other words. But the beginning of this terminology is that when this terminology started, and this was, by the way, before O-minimality started, we did have a very vague idea that there is such a thing as dimension in these structures. So it came later with developments in classification theory. Okay, and there are various types of minimal structures. So the historically the first and actually the most exemplary kind of minimal structures, these are strongly minimal structures, and they are inside the class of categorical structures. And then O-minimal structures, which with which you already are acquainted with, and C-minimal, DP-minimal, and so people go on working on this and making sense of this. Okay, the most important, well, at least to me, is this trichotomy principle that I suggested many years ago in a form of conjecture, which I can say from outset was repeated, a counterexample was found by Khrushchevsky to this as a general principle, but it turned out that in many cases it usefully proved to be correct. Okay, so what is this trichotomy principle? You see the slide. It says that that minimal structures actually come in three non-intersecting classes, and there is in each of the classes we use a specific a procedure or notion of what reducible to means. And to really understand what it means that in terms of definability, it is, or we rather would say, interpretability. So you can use this formulas, the first order formulas that you already are acquainted with to say things about the structures which essentially as if you are using the language of first case fields, and the second class, it is a language of modules, which means, of course, that you have some addition and multiplication by elements from a division ring K. And the third class is a G set. And here I immediately give you a suggestive example of how it can look like. So if you take upper half plane and think of it as a universe of a structure, and the only relation that our language sees in the structure is the action by elements, and you should think of it as element by element of this classical group GL2Q. Right. So this, as I said, is not true in general, but and the fact that it is refuted is very, very important, and more than half of the rest of this lecture would be discussion of the consequences of this procedure that refutes this trichotomy principle. And but in some cases it proved to be true, and the first case was by Hrushevsky and myself for specific class of so-called Zariski structures, which are very similar to structures that you can find in absolute algebraic geometry or complex algebraic geometry, and so it's very interesting class with some consequences. So Hrushevsky found a brilliant applications of this and similar results that he himself then found. So these applications in arithmetic, like the analysis and proofs of some cases of Mordaunt conjecture and Manin-Mumford conjectures. And in terms of O-Minimality, there is again what I would consider quite important in the context of the current workshop result of Peterzl and Starchenko about trichotomy of for O-minimal structures. I will say a few words about this in the next couple of slides. Okay, so I show now some simple illustration of this phenomena of this trichotomy that you can see in the context of algebraic geometry. So so consider just planar curve C. Well, it doesn't matter that this is affine plane over the complexes. It works with any algebraically closed field. So it is useful to assume that it is irreducible, smooth, and we set a structure on this curve. So the curve for us now is just a set, right? So we only see it as a set, but the way that it sits inside this affine plane, we can also say about several points on the curve as they being collinear or not. So this is the only relation in our language that we actually see. And now you see what will happen is that if this is okay, so how degree of the curve plays out in this picture? So if the degree is low, is less than 4, then being collinear would for 4 points would of course imply that at least 2 of them coincide, and that's all right. But in the case when it is say degree 1, if it is just a point, if it is just a line, it is just a straight line on the affine plane, then the collinearity is just a trivial relation, of course. And so we have here a situation of trichotomy that can be exactly well. You see it in the slide. So the first case is exactly the case when our structure interprets the field. So algebraically closed field in this case, of course. So the second case is a case that corresponds to a module. So of course the degree 3 curve, it is well-known procedure of how you identify a group structure on such a curve, and the point of this statement on this slide is that there is only this structure and nothing else. But whereas in first case, you would actually be able to recover the whole field. This is not quite trivial. This in a slightly more general setting, it is a special theorem of a very useful theorem of Rabinovich, Evgeny Rabinovich of 1988, which turned useful in some important applications. So, for example, this application is related to what Bogomolov and Chinkel called the abstract Torelli theorem for curves of high genus. Okay, and
Can I ask a question?
Yeah, sure.
So is the relation you imposed just for quadruples of points or arbitrary number of points?
No, it is just 4 points. It is you don't have to consider more than 4. It is yeah. So it is for a relation.
Okay.
Yeah, and of course in the third case you have something very simple. We call actually this sort of structures trivial type geometries. Yeah, so here is it is just illustration, and I think it's good to think about this and maybe try and do some exercises about this. Actually, I started many years ago in 1970s with my students working on their master work to do special cases of this. Right. So now let's talk about Peterzl-Starchenko trichotomy theorem. So this one is much more complicated. I mean, in formulation, and this is a kind of a final classification result. So what do we have? We have only three possible cases, right? So the case one, which correspond to the full case, so to say, when we would be able to recover in abstract or minimal structure. So the important thing is that you should have in mind that we started with no knowledge about there being any field in the background. So it is the definition, if you remember it, it only requires that you have an ordered set, and that on this line, this ordered line, you can only define intervals and nothing else. So finitely many intervals are what your definable sets look like. And so the first case says that if certain conditions are satisfied, then you are in first case. And this would mean that locally, right? So one has to understand what it means. You see, because the situation would be such that one interval is not necessarily linked to another interval. So the abstract definition is such that it allows no connection between two intervals. Of course, if you have addition, then you have shift intervals, and hopefully when you overlap intervals by shifting, then you would see that this is essentially the same structure on these two intervals. But in general, it is not the case. So we should be careful what the means of locally is here.
Can I ask a question?
Yeah.
So do you have in mind just a union of two real close field where one copy is, let's say, bigger than the other? Is that the kind of non-local structure you have in mind?
No. What I have in mind is that you can put side by side two intervals. So on one interval, you will have a piece of the field of reals. So you have partially defined addition and maybe multiplication, right? So partially, what I mean is that if x plus y goes beyond the interval, then you take it equal 1, for example, right? Well, this already would allow you to recover the field of reals, and then another interval which is a continuation of the formal continuation of this interval, but has no relation to this. So is doesn't have any structure except for order relation. So there is no any trace of the field of reals there. That's how it can be, right? Well, let me show you. Yeah, maybe here I have. So it can be that you have something like this. Okay. So and this is ordered, and this is a piece of actual reals, and this is for example a piece of any other ordered set, and you see, formally you can consider it as an O-minimal structure. Whatever strange it looks, but that's a possible case. Okay. Right. So the yeah. So what is the f here? So this f is our well, in this case you can think of this as basically some family of functions, right, or relations. So something quite general. But of course, the general assumption also is that everything here satisfies this definition of O-Minimality. Right. So the second case is that apart from this f, you have ordered module over division ring. So, for example, over Q. So, which gives you a divisible group, just ordered divisible group, and then the condition on functions must be that they are of sublinear growth. That there is some so for every function there is an n in the division ring, which gives you such a bound. And the example again you see in the slide. Okay, what is very important here is that you see, if this assumption of sublinear growth is not satisfied, so you have some fast-growing functions here. So, for example, exponentiation. So, if in this place you have an exponentiation, then you jump into case 1. You see, that's a very non-trivial corollary of this classification, and this is I think it is by Miller. It is pre-Peterzl and Starchenko theorem, or maybe it was Miller and Starchenko joint statement. Okay, and then the third case, it is when you cannot even have addition. You just have an ordered structure with some functions on it, but the functions are very simple. They are essentially one variable functions. So you cannot have two variable function, which is actual two variable function. So the example you see here on the slide is the reals with order and exponentiation. If you start with this sort of structure, it is what I already called structure of trivial type geometry. Okay. Now a few words about compact complex manifolds. Again, in this case, the trichotomy principle does hold, and I cannot be very precise here, but it is at the level of typical examples. Some of these are just examples, and some and part of it is a precise theorem. So so the three classes, the three classes that principle lays out here would be of this kind. So it is the first class where you can recover a field is complex projective varieties and a little bit more complicated thing, which is Moishe-Zon manifolds. The second class are complex tori, which do not have structure of abelian varieties. So it is kind of a generic tori. And yeah. And the third class is Hopf manifolds, which so I cannot say, maybe some people know answer to this question, where the third class where you have in our classification this trivial type geometry has to be non-Kähler. Probably yes, but I don't know if this is a theorem. Yeah, it's probably open questions here, which of course the questions in classification of compact complex manifolds. Okay, so once again, coming back to this trichotomy principle, now
quick question. So in the first case, you said Moishe-Zon manifolds. Do you allow just singular Moishe-Zon spaces, or does it not matter in your theory?
Well, no, manifolds probably is important here. This being non-singular, but I'm not very sure. Well, it depends on how you exactly formulate this. Probably a few singularities wouldn't matter, but and by the way, it's this sort of things also work with compact complex spaces. Mm-hmm. So yeah. Okay, let me go on. So this slide with trichotomy principle again. Now I show along with these three classes, I want to also you to pay attention to in each of the classes there is a specific another kind of dimension, not the dimension of variety, but closely related to it, a dimension in the sense of transcendent degree in the first class, right? So it's something that everyone knows. Then in the second class, it is linear dimension. And in the third class, it is a number of G orbits. So if it is really the G set in a full sense, then it is a number of G orbit. By the way, when I give you this third kind of example, it is not necessarily has to be a group, but can be kind of remnants of a group, like when you look at modular curves, you have Hecke orbits on them, and these Hecke orbits come from the origin of Hecke orbit is the action of GL2Q on the covering space. But what we see on the modular curve itself is a bit different kind of phenomena. Okay, so these are also something that we call dimensions. Oh, there is a misprint here. Never mind. So this actually play a very important role because we use those to characterize so-called combinatorial dimensions that sit on these minimal structures in each case. So this notion of dimension and corresponding dependence, so like a transcendent degree corresponds to the algebraic dependence. So the points in the field being algebraically dependent or independent. The linear dimension correspond to linear dependence, of course. And the G set dependence correspond to being in different orbits. So what we come to at this point now is that Hrushevsky came up with the idea of a counterexample to this trichotomy principle by playing with these three types of dimensions and making funny combinations out of these dimensions, but he actually it was very ingenious. It is still something that I admire very much. It is not any combination of these dimensions that. Oh, sorry. What? So what he has introduced is so you see here this one possible combination. So you start well, you have a field F, and you want to put an extra function into your structure over your field structure. You want to put an extra function, which if you want to oh, sorry. Oh, something bad happened. Oh, yeah, I'm here. Yes, so so you see, you want this function in order for this structure with this new function to be strongly minimal. It must be chosen in a very special way, and so Hrushevsky's idea was that this function should satisfy a certain kind of pre-dimension inequality, and then you put this combination of dimensions. So you take you consider the field which is generated by a tuple or a finite set of elements x bar. You take the image f of x bar. So you have some finite set of elements. You generate a subfield. You ask what is the transcendence degree of this subfield, but then you also separately look at span of this finite set, Q span of this finite set as a vector space, and ask what is the linear dimension of this span. and then you take this difference. And the value that you get is your kind of counting of this effect of introducing this function f on this tuple of elements delta. And of course, if you want this to become some sort of dimension, you would also want this to be non-negative. Okay, and then you have this pre-dimension inequality. That's what we call a pre-dimension inequality. Another example of this would be this one, where instead of linear dimension, you take just to count the number of elements in X, number of distinct elements in X. And this is as good as the first one. Actually, it is easier. The second case is easier to deal with, and the first case is doesn't quite fit into the Hrushevsky construction. But we will come back to this first case as well. Now, what then Hrushevsky proves that for certain forms of this pre-dimension, after you undergo certain procedures typical for model theory, but very non-trivial really, you get a strongly minimal structure, categorical structure, which contradicts this trichotomy principle, and this condition. Oops, sorry. So this condition that this mentioned in this Hrushevsky theorem works well with this second example, and does not really work with the first example. Now, the observation that well, maybe before we discuss this observation, I should tell you why it was such a fuss for us, because trichotomy kind of suggests that everything is so nice in classification theory, and we have some leading idea about this trichotomy principle. And then when this Hrushevsky counterexamples came around, so we were quite puzzled really, and the questions that people start asking about, it is a pathology. What so is this the universe of mathematical structures is full of pathologies, or what it means, and so on. And now we can go down to this observation, and what this observation is, you have time already to see, is that this harder one of this pre-dimensional inequalities in a slightly more specific setting is nothing but the statement of Chanel's conjecture. So this inequality is equivalent to this inequality that transcendent degree of the field generated by n linearly independent elements together with the exponents has so transcendent degree is as at least n, and this was an important moment where we started to realize that what Hrushevsky introduced by his fully abstract, actually combinatorial methods and combinatorial thinking is something that is deeply rooted in in classical mathematics. And then it took some years to produce a precise statement that follows from this observation that you can adapt Hrushevsky construction. So the original have to be adapted, and the main adaptation of this is that you have to work with not the first order language, but you have to extend into languages that allow, in some cases, allow infinitely long conjunctions and correspondingly disjunctions. So something like this, but in fact, a little bit more is also required to satisfy this this theory. So the formalism that satisfied this theory. And of course, a very important thing is that you not only you have this analog of this structure, but it is also a axiomatized by concrete axioms, which are a product of this Hrushevsky construction. So you see the Hrushevsky construction, because you follow certain concrete procedure, you know what properties you construct, and so you get an explicit axioms for resulting structure, and then you also prove that these axioms have a unique model, and so the proof I mentioned here. Well, actually, I produced this statement and even published it. It was in 3 papers. I think by 2003 I published this. But then it turned out that there were some gaps in this, and then with some of my students, I went on to fill in the gaps, and some other people joined, and so the clean proof came only by 2012, and the proof actually very much relies on a very advanced Shellach's technique, extending categoricity theory to this infinitary setting, and also it requires some non-trivial number theory results. Well, in this case, it's quite simple number theory results, but in other similar cases, for other transcendental functions, you would need some stronger, well, depending on what functions you are dealing with, some other number theoretic results. So now quite a lot is known about this, but the story is far from being finished, and I will continue on in my slides. But before I go to more general cases, let me just show you some concrete axioms that are the results of this construction and analysis of this construction. So, of course, you would have just a usual algebraic assumption about the exponentiation, that it is a homomorphism from additive to multiplicative group with the kernel like this. And already in here, when you want to say that it is exactly this kernel, you have to use some infinitary statement. It's not first order. Then you formulate Chanel's conjecture, and then so Chanel's conjecture is just you know, this Hrushevsky inequality, and then you have as a very subtle consequence of this construction is this existential closeness. So we technically we call it existential closeness, but Angus MacIntyre noticed that this is essentially nothing but a Nullstellensatz for algebraic exponential equations. And so this can be stated in very precise terms, but it would take a couple of slides with some technicalities. So roughly speaking, what it says is that you have some polynomial exponential equations, and you can if you can check that in a certain algebraic way that they do not contradict Chanel's conjecture or do not contradict the Hrushevsky inequality, then this must have a solution. Okay, so for complex numbers it is not known, but people went into looking into this, and many special cases were checked to be so, for example, one variable case is established in full. So if you have very complicated expression, well, equation that is just in one variable, then this does have an equation, assuming that it doesn't have some degenerate form. Well, this the last one, countable closure property, it is it does hold for the field of complex numbers with exponentiation, but you have to postulate it for general case. Well, and then you have, of course, a natural conjecture that if you take the field of complex numbers with exponentiation, so plus, times, and exponentiation in your language, to then up to isomorphism, the unique model of the axioms on the previous slides, the one that is of cardinality continuum, it satisfies all this, and it is the unique model of all those axioms. We know from our theorem that the model can only be unique, and the model does exist. What we don't know is that the complex exponentiation does satisfy all these conditions. And of course, the first one that we don't know is whether it satisfies Chanel conjecture. And the second one, this Nullstellensatz, is another unknown. And well, there is now some understanding that actually the two are quite linked. So it is well, it is quite clear that the second is a kind of a dual of Chanel's conjecture. But well, anyway, it is quite interesting. But now in explicit consequence, if you assume that complex numbers satisfies those axioms, then you have this the following property, that the projection of a curve of exponential, this analytic curve that is given by exponential polynomial equations, so its image on the complex plane is its projection on the complex plane is covers almost everything. So it has at most countable complement. or it could be just a point, of course, if it is, it could project just into one point. Right. So this is some open problem, and some people like Alex Wilkie made quite significant inroads into solution of this problem, but it's still open. But you see, this this conjecture above suggests that this is the case. Of course, it is not true for arbitrary analytic function in place of exponentiation. Arbitrary holomorphic function in place of exponentiation. There are counterexamples, but you know, exponentiation and similar functions probably have this property. Now let me. Yeah, I'm coming close to the end. Let me now briefly mention also something about channel, but in a proven form, and this is Ax channel, and it is proven in the context of a very important structure that I also mentioned before, this differential field. And the statement is this one. So instead of exponentiation, of course, we talk about solution of this equation, which obviously is a differential equation for exponentiation, modular constants. And then what Ax proved is this kind of Hrushevsky inequality, and yeah, so this is a very useful theorem, as I'm sure that Bruno is going to mention and illustrate its use. Yes, but what is also important is that in the same context, in this environment of differential fields, one also knows that for some other differential equations, the solutions for those differential equations, we have similar inequalities. And well, I think about those which have this property, those differential equations, as a kind of special tame differential equations. And I think it's very interesting, very important to understand. So, which ones are those? So, is there some general theorem that covers all the cases, that tells us that for some tame class of differential equations, we have this property? And I know that some people are working towards this question. Okay, and finally, you see, we already mentioned that this Hrushevsky predimension is of very general type, and because we have a lot of examples also of this phenomena in mathematics. We can look at, we can ask, what does this suggest for mathematics, for geometry, and so the way of looking at it is this. So we can put Hrushevsky inequality in this form. So we have transcendent degree. Well, so there is supposedly some choice of transcendental functions, or whatever you find appropriate for your Hrushevsky construction. So we worked out this, for example, for a number of elliptic functions. And then there is a corresponding dimension notion. So for exponentiation, this is linear dimension. So you see, I put this subtraction onto the right. So there is no zero inequality with zero here. But in this form, it looks more like a Grothendieck period conjecture, and of course we know that Grothendieck period conjecture. So Andre and his students produced some results that illustrate that the meaning of Grothendieck period conjecture in the context of Chanel conjecture and its extension to elliptic functions. And in all these examples, these two work in a very, very similar way. But my feel is that that this one is more general. And the one reason why I say this, you see, so this, for example, can include counting the number of orbits, right? So this is very simple pre-dimension. And in my understanding, this is not the case. So this is basically, this one basically covers the abelian cases. Or maybe I just don't understand this full enough. Anyway, it is very interesting to think about these two together. Right. And finally, the very last thing. So so this brings us at last to the issue of axiomatization. You see, in all these examples, really, if you again work on this from a logical point of view, it is you analyze your axioms and you find that some strange thing is happening. So in some cases, this pre-dimension inequality, well, you want this pre-dimension inequality to be finely axiomatizable. Well, it's not exactly the, well, first order axiomatizable is the right word for this. And this requires some strong uniformity. And this uniformity is really, you know, it is a statement about anomalous intersections. And this is, so this is how we on the model theory side came to think and ask about this problem of anomalous intersections. And of course it is, there is the conjecture that comes from Shmurov varieties people that worked in this direction, following some very concrete analysis of concrete examples. And so there is this celebrated Bambieri, Masser, Zanier results for abelian varieties in, well, some more specific situations. And there is now some solution of Andre Oort conjecture, but these are concrete technology and concrete examples. What is, I think, what is interesting that on the logic side, this came from general philosophy, and it is quite amazing that this general philosophy turned out to be just on spot. And yeah, so this is my last slide, and so thank you very much.
Yeah, thank you, Boris, for extremely interesting and very clear set of lectures, 2 lectures in the mini course. I'd like to see if there's any questions that anyone would like to, or comments that anyone would like to ask of you.
Yeah, I have a question.
Yes.
Hi, Boris.
Yeah.
My question, let me put on my camera. My question relates to the function field version of Chenuel's conjecture, which was formulated by Laurent Denis, I think in the 90s. Are you aware of this work?
No, but what you mean, Chenuel's conjecture for function fields?
Yeah, you have the Karlitz exponential in the setting of function fields, and you can formulate the exact analog of Chenuel's conjecture. And actually, there's been some recent work on this by Federico Pellerin, I think in 2017. But anyway, I'm wondering if yourself or other logicians or model theorists have attempted to apply the ideas of pseudo-exponentiation in the case of function fields of positive characteristic.
Well, certainly not me. No, I don't know about this. Yeah. So, well, I would think that this is close to the axis approach, but which of course turned out very successful. But no, I cannot comment on this.
Well, it might be interesting to explore because,
Yeah,
as we know, sometimes problems are easier to tackle in the function field setting.
Okay. Yeah, thanks.
Okay.
Thank you. Are there other questions or comments?
Maybe a question for
Sure.
clarifying the philosophy. So I'm not sure if this is what you meant, but it seems that you meant that the interesting minimal structures from the point of view of geometry are those that fail the trichotomy. Is that true?
Well, okay, no, kind of, yeah, they are interesting in the sense that they are conjecturally of analytic nature. Okay, so so the ones that satisfy trichotomy, as if you return to the original slide on the trichotomy, you would see that they are kind of classical. In fact, so all the 3 cases of trichotomy were in fact considered by van der Waarden in his you know, in his book on algebra of 1930s. That's where this research on dependencies and this sort of combinatorial dimensions come from. And so these are also called matroids. So this is very classical stuff. And those which do not satisfy trichotomy, they are, well, they are of some mysterious nature. And so some people say that maybe it is possible to extend trichotomy principle to what is a right word for this, for formulate 4 cases. And the 4th case, yeah, so if you try to formulate the 4th case, then it is difficult, but maybe the 4th case is a kind of analytic functions are present. But if you start thinking in this direction, then the next question would become what analytic means in this general context, because actually it is quite possible. So Tim Gendron just mentioned that there is this funny analyticity of this funny exponential functions. So there is a non-Archimedean context So you have non-Archimedean exponentiation, for example, and possibly other constructions of this kind. So in fact, you are here would approach probably a possibility of formulating what analyticity in this very, very general context means. So someone asked yesterday the question about a similar question in the context of O-Minimality. You see, whether the functions that appear in O-minimal context, they are all analytic. So this is kind of the similar situation. They are not analytic. It is a broader class than analytic. There are this. So Alex Wilkie found that what is Carleman-Danjois classes of these functions, and so something like here could be expected in this case.
Thank you.
Yeah, thank you.
Yeah, thank
Any
you.
further questions? If not, then perhaps we can thank the speaker, and we will have the next talk in about 8 minutes at 10:15. So.
Thank you.